we quickly recapitulate our discussion on the knife Bayes classifier. What we did in the knife Bayes classifier was the following. We made the independence assumption, that means, if you have two variables a and b, if they are independent, the joint probability is product of their individual probabilities. So, as you know that if you have two, both a and b, we call it a joint probability, and if the individual a and b, we call them marginal probabilities, the marginals. Okay. So, for example, in this particular case, if these 4 attributes give birth, can fly, live in water, have legs, are independent, we have probability this give birth equal to yes, let me I will write it at b equal to y, and can fly equal to no, and so this comma is an and actually, live in water w equal to yes, and have legs L equal to no. This probability given say mammal, if these attributes, that means whether an species gives birth to a young, does not depend on whether it can fly. Similarly, it does not depend on whether it lives in water or have legs. So, if the attributes are independent of one another, that means what value one takes no way depends on what value the other variable, other attribute takes, then we can write this joint probability as probability give birth yes, fly no, water yes, legs no, equal to product of their marginal probabilities. That means, probability birth equal to yes given mammal into probability fly equal to no given mammal, probability water equal to yes given mammal, into probability legs equal to no given mammal. Note that we can write this only when these attributes are independent. But if we can write it this way, then definitely there is an advantage. Okay. So, what is the advantage? The problem we faced in the in finding out the probability of the joint 4 attributes taking on certain combination of values is that there are only few examples out of all these 7 mammals who have exactly this 4 combination. Okay. So, we have a kind of absence of training set. We have not seen what happens. These we have not encountered before what happens in this case. But each of these individual cases, that is, it is mammal and give birth equal to yes, it is mammal and fly equal to no, each of these individual cases, they are not so rare. They are not so rare. Okay. So, if you find out, actually you can see that out of 7 mammals, 6 give birth. Similarly, 6 cannot fly. Okay. 2 lives in water. Okay. So, in other words, I get a better estimate of the joint probability by expressing it as the product of the marginal probabilities, which I can again remind again that which I can only do if they are independent. Okay. And once you estimate this, rest of the thing is same as that of the map classifier. Okay, check, compare the two classes, whichever is higher, put in that class. In fact, in practice, we in extreme case, what can happen is that still you see the one thing about this, it is that I am expressing this probability as a product of 4 probabilities. Okay. So, even if one of these 4 probabilities goes to turns out to be 0, the entire thing becomes 0. So, it is a product. Okay. So, it may happen that one of the probability is small, okay, but I want this small thing to be represented not by 0, but by a small epsilon value, small value. So, that is the idea of smoothing. The idea of smoothing. So, if my actual estimate is this, and if this is 0, I do not make it 0, I add a small term 1 and divide it by C. So, this entire thing will be small, but not 0. Okay. So, it will be small, but not 0, and it will not collapse by after product the entire thing. So, in practical application you have to often use this. Okay. So, I'll all this looks very fine, this is a very attractive, in fact this is one of the commonly used also. So, I will maybe give you an popular example. So, it is like this, I have by the words it contains. Okay. So, these are the so called attributes. Okay. So, basically I will take all the words W1 that English has, Wm, and an email, let me call it E1, is represented as whether this word is present, I write 1, otherwise 0. Okay. So, this binary vector is a representation of an email, and my task is from this binary representation I have to classify emails into 2 classes, spam or non-spam. Okay. So, how I do it is that I collect lot of spam mail, I apply just like I did in the previous example, count how many times W1 is yes, count how many times W2 is yes, multiply them using the naive Bayes assumption and get the total probability it is a spam, or and similarly the total probability it is a non-spam, and whichever is higher I put it into that class. The underlying assumption is the probability of words appearing is independent of each other. So, maybe it will happen after I do this, maybe the spam emails will have a higher probability of having words like lottery and dollar and so on. And maybe non-spam will have a higher probability of other words, a meeting and so on. Okay. So, this is naive Bayes is one of the most common industrial classifier used, okay, and it is pretty successful also. All right, but there is no guarantee that this independence holds. That means, there is no guarantee that P of A B, two attributes equal to okay, but maybe there is a less strict condition. Okay. Condition known as conditional independence. So, independence is this C is not there. So, conditional independence says that individually I cannot write this, but I can write this once I have another variable C and I have observed the value of that variable. Okay. So, in other words, I can write probability of A B given C is probability of A given C into probability of B given C. Okay. So, in more general terms, if you have I variables A1 to AI, probability of their union given C is the product probability of their marginals given C. Okay. So, this is less strict. So, you can think of this like this. Suppose I am tossing two coins, unbiased coins, okay, and just two outcomes, either 1 or 0, head or tail. And if the A is probability, the first coin is tossed gives head, B is the probability that second coin toss gives head, and other combinations. Okay. So, you see they are independent, because what is the probability together both will be head, I can write as the probability of one is head and the other is head. So, it will be, if they are unbiased, it will be 0.5 into 0.5. There is actually another way of writing this. This actually you can write it as probability if A is independent of B, probability of A given B is just probability of A. Using the definition of probability you can derive it. Okay. By the way, so this cross is not there. So, if they are independent, they are equal actually. One way of looking at this is that B gives no information about A. Knowing what the value of B is does not help me predict what A is. When I toss two coins, that is the case. What is the outcome of one coin does not help me predict the outcome of the other coin. But if there is a third variable which helps, then I call it as conditionally independent. Let me take this example and tell you. let there be two persons A and B, and the events be they are both of one of them comes home, A comes home for dinner and B comes for dinner. And the third event is that C is that a snowstorm hits the city. Okay. So, in this case both have low probabilities of getting home, but they are still independent. Okay. So, whether A is late does not tell you whether B is late. Okay. So, if they are say quite different, they are not related in any way. So, they live far away from each other, then they are independent, even if there is snow or no snow. The outcome of C does not affect. Okay. So, one does not a outcome of A, whether A has come home early does not help me predict whether B will come home. So, in this case they are independent. So, I can write probability for the first case. I can write that. Okay. But suppose we know that they stay in the same neighborhood and take the same transport, then I can use the information about A to predict B. If I know A is late, I know that probably B will also be late, because they use the same transport. Okay. So, they are no longer independent. So, in the second case, so first case is conditionally independent C I, the second case is okay, not C I. Pictorially this will look something like this. Okay. So, I have 3 events, red, blue and yellow, and each cell is a possibility. So, all these, whenever the blue event happens, all these blue cells get a color, and for red and for yellow. Okay. So, in this case you see, if y is given, R and B are independent. If I know y, if I know y has happened, I can tell something about the relative probabilities of A and B, R and B in this case. All right. So, this is an example. So, this conditional independence, that this fact that probability, let me write as x y. Conditional independence is written by this notation, that x some perpendicular y given z. So, this is the symbol for independence. Okay. So, plain independence is x independent of y, this is just independence, x, y, z are random variables, and this is conditional independence. Okay. So, if the conditional independence holds, then I can write the following 3 things. I can write this, x equal to x means x taking on certain value, I can symmetrically write this. Okay, so x independent of y means y is also independent of x, and of course, the definition I can write this. So, I give you a small exercise. So, I have 3 variables: a student is smart, a student studied, and the student is prepared for an exam. Okay, and these are the probability values. That means, if a student is prepared and is smart and studied, so this is actually prepared, and studied and smart. That probability is 0.432, and this is prepared and not studied but smart is 0.16. Okay. So, what we are supposed to do is to figure out 2 things. First thing, find out from this margin also I am actually looking at the prepared, smart, study. What are the marginals, which things add up to 1, what are the conditionals that can be there, and what are the conditional independences that hold. Okay, please do this exercise, you will get a better idea. I will put up the solution. All of you please note it down. For the moment write it down, I will put it up in the exercise set also. Note that it is 3 variables, so all combinations, 8 combinations. Okay. It turns out that this kind of conditional so this is one example, in general there will be many. You can capture using something called a directed acyclic graph. All right. So, every node is a variable and the following holds, and the following holds. So, I hope you understand what is a parent, ancestor and non-descendant in a graph. So, this is a directed graph, there is a directional arrow edge, and every attribute or variable is a node of the graph. So, I can represent, we will see in our next lecture, is that I can represent conditional independences whatever are present in among the attributes by a directed acyclic graph like this. There is something called a Markov assumption, which tells that it is memoryless, it forgets other variables. Okay. So, I can capture using this and have a more complex type of Bayes classifier. So, in summary, this is what I have. I have some robust probabilistic classifier. It can handle irrelevant attributes as well as missing values. You can have the independence assumption, makes life easy, naive Bayes, or you can have a directed acyclic graph capturing conditional independences. Okay. So, this is the summary. In this is the basic introduction to Bayes classifier. In our next class, we will move on to the conditional independences and Bayesian networks, not just classifiers. Thank you for today.